All right, thank you. Thanks for the kind introduction. Hello, everyone. Thanks for attending my talk today. I'm currently a postdoc working with the reduced order model team at CASC. Today, I'm going to talk about some recent progress in using reduced order models to accelerate the MFEM simulations. So the results presented today are mainly contributed by the reduced order model team, which includes Dylan, my mentor Yongshu, and Pranav, and our former member Kevin. But we also like to take this chance to recognize our wonderful collaborators. So I will begin with a brief introduction to reduced order modeling, which is a data-driven approach with the goal of accelerating physics simulations without sacrificing too much accuracy. Some reduced order models are purely data-driven, while the others utilize the original governing equations to make the methods physics-aware. Suppose we have a high-fidelity model or experiments with different scenarios, such as varying design parameters or uncertainties. So it will be, in general, expensive to simulate or carry out these experiments in a multi-query application. And we will collect this solution data as some representative scenarios as snapshots, and we will compress this data, which results in some low-dimensional structure for representing the solution manifold. And this will allow us to formulate the small dimensional algebraic systems and solve for an inexpensive approximate solution in a generic scenario. Since this talk will focus on the use of reduced order model techniques to accelerate the MFEM simulations, we'll use some fantastic MFEM examples and mini apps for our numerical studies. For instance, we have the linear and static PDEs, including the Poisson equation and the linear elasticity. Next, we have a linear time-dependent PDE, the affection equation with the discontinuous Galerkin method. Then we'll have the more advanced nonlinear time-dependent PDEs, which include the nonlinear elasticity, the nonlinear heat conduction, the Euler equation with discontinuous Galerkin method, and finally, the Lagrangian hydrodynamics. So the reduced order models are implemented in our open source C++ library called libROM, which is contained in this GitHub repo. We also set up a web page which includes the useful documents, examples, and tutorials about reduced order models. So as we just mentioned, the first step in reduced order modeling is to compress the collected data. And one of the most simplest and powerful compression technique is the singular value decomposition, SVD. Though there are different implementations of SVD in libROM, I will focus on the static SVD for simplicity. So suppose we have collected M solution states with high dimension, capital NS, and assemble it into a snapshot matrix. So for MFEM vectors, it can be done with very straightforward libROM syntax. The singular value decomposition is to factorize this snapshot matrix into a product of three matrices: the left singular vectors, the singular values, and the right singular vectors. Then the Eccles-Young theorem tells us that the best rank K approximation of the snapshot matrix is obtained by summing up the rank 1 matrices corresponding to the K largest singular values. So this suggests that we can use those left singular vectors, which we call the high energy dominant modes, for a spanning subspace to approximate the solution. And in practice, we use an energy criterion to select the minimum number of sufficient modes for an acceptable accuracy. So we will present how a projection-based reduced order model can be obtained from combining the data and the governing equations. Here we consider the proper orthogonal decomposition approach for general nonlinear dynamical systems, but the procedure is actually very much alike for static or linear PDEs. So we'll use a low-dimensional affine representation for the solution representation, where the basis phi comes from the singular value decomposition on snapshots. Now the number of unknowns becomes the number of singular vectors included, which is much smaller than the original space. Then this system becomes overdetermined. So we have to reduce the number of equations to make it well-posed. We use a Galerkin projection onto the column space of this basis to obtain a small dynamical system. Then we can do our favorite temporal discretization, for example, by the simplest Barrow-Euler method. The matrix multiplication here means we need to do some MFEM actions on the basis vectors. And this can be achieved by converting the basis we get from libROM to an MFEM dense matrix. And we should emphasize here that the basis is defined in the global domain, in contrast to the local degree of freedoms as usual in MFEM. So everything looks good so far. However, in computing the update, we still need to lift the reduced order coefficient to the full state, compute the full order vector F, and project it back to the column space. So this operation scales with the full order model size, which will hurt the speed up. Therefore, we need the so-called hyper-reduction techniques. So in libROM, we have different algorithms for hyper-reduction, which are quite MFEM friendly, and we will introduce more about it right now. The goal of hyper-reduction is to reduce the cost of nonlinear term evaluation. So similar to the solution state, we will approximate the nonlinear term in a subspace. We use the discrete interpolation technique, which is to select some sample entries of the nonlinear terms to evaluate. And we will find the best approximate candidate in that subspace which match these selected indices. And this is actually just a pseudo inverse. So replacing the nonlinear term by this approximation may make the system looks more complicated at the first glance. However, the operator which maps the sample entries onto the solution subspace can be pre-computed in the offline phase. It is a small matrix and it is inexpensive to store. In the online phase, we just need to evaluate the sampled entries for the room time machine. In many applications, these nonlinear terms may involve the spatial derivatives, and the neighboring nodes and elements are required for this nonlinear term evaluation. So we call these connected nodes the sample mesh, and the nodal or the zonal values on this mesh is all we need for the reduced order models. So in libROM, we have a class which is specifically designed for the sample mesh of MFEM applications, which is much like the par mesh in MFEM. So after all, the story is, since we don't need to record and evaluate all the entries in the high dimension, every computation is of a reduced order, so we can expect a speed up. So one crucial remaining question is how we determine this sampled index. If we randomly select this index, we may end up with inaccurate approximations of the nonlinear terms and therefore the solution. So we note that the hyper-reduction actually introduced an oblique projection of the nonlinear term to the subspace. And therefore, the oblique projection error shall be minimized among all sets of sample indices. However, the true minimizer depends on the nonlinear term vector, which is invisible. Luckily, we have derived some suboptimal error bounds, which are universal for all source terms, and the constant is independent on the sampling indices. So we are satisfied with minimizing those error bounds. There are different approaches in this line, including the DIME, GANET, and SOPT. And the precomputation of the sampling indices using these algorithms are all implemented in libROM. So, in another perspective, when it comes to finite elements, we can consider the variational form and the quadrature rules. The MFEM action on the basis can be formally understood as a global quadrature rule on these basis vectors. And reducing the number of rows is equivalent to reducing the number of quadrature points. The empirical quadrature procedure is introduced to find a set of quadrature points and weights which gives the best approximate reduced quadrature rule to the original global quadrature rule at the functions of interest. So this optimization problem can be solved by non-negative least squares efficiently. We have applied this hyper-reduction idea to the nonlinear heat conduction. But more interestingly, this idea is not only useful in nonlinear model reduction, but any cases where we have more quadrature points than constraints. So Dylan has implemented this idea to accelerate the NURBS quadrature in MFEM and observe a 6x speedup. So here we present some selected numerical results on projection-based reduced order models for several MFEM examples which can be found on our libROM webpage. They all have promising accuracy and speedup. It is worth mentioning that all these results here are predictive cases, which means the problem parameter considered in the online phase is different to that in the offline phase for generating the snapshot data and construct the reduced order model. And moreover, the accuracy of speedup is actually of competing interest, and we can actually further increase this speedup by relaxing the accuracy through using less basis factors. So we have also applied the PROM to Lagrangian hydrodynamics, which is discretized using the curvilinear finite element and artificial viscosity, which yields a system of nonlinear ODEs describing the conservation of momentum, energy, and the equation of motion of the Lagrangian frame. So here we will discuss a projection-based reduced order model for this system. First, we will build a reduced solution basis by SVD separately for all the three fields, and then we perform the Galerkin projection. Second, we will use the discrete empirical interpolation method separately for the two nonlinear terms in the conservation of momentum and energy. The last equation is linear, so it does not need any hyperreduction. Furthermore, for the nonlinear term basis, instead of using another SVD, we can use the SNS technique, which is simplifying this reduced order model system. Then we can apply some time matching scheme. So we have tested on several benchmark problems, including the Seedorf blast explosion, Taylor-Greenville test, Rayleigh-Taylor instability, Gresham-Vogt test, and triple point expansion. It's worth mentioning that due to the effective phenomena in Lagrangian hydrodynamics, we developed the time windowing and distance windowing approaches to get these outstanding results. But we will leave the discussion of these approaches later. One great thing about these reduced order models is that its speedup actually increases as we apply it to larger scale problems, so make it attractive for such problems. As an example, we see it in the H refinement of Rayleigh-Taylor instability problem. So while these projection-based reduced order models are great, we often need to do invasive changes to the original solver since the governing equation is required. As an alternative, the non-intrusive reduced order models are purely data-driven, which is easier to work with. So we also implement and develop these methods in libROM. One of the simplest non-intrusive method is the dynamic mode decomposition. Suppose we have a sequence of snapshot data which are of equal time stepping. The DMD seeks a linear approximation of this discrete dynamics. So the procedure goes as follows. First, the snapshots are assembled into a pair of input-output snapshot matrices. The truncated SVD is carried on for the data compression of the input snapshot, which allows us to find a load rank linear approximation of the dynamics in the subspace. Then we will do a spectral decomposition on the reduced dynamic operator to get the dynamic modes, which diagonalize this matrix and allows us to do many times of this matrix multiplication to get any prediction easily. So one important remark is that the DMD approximation does not rely on the original physics, which is a suitable candidate for general experimental data and very high fidelity and complex simulation data. We have applied the libROM implementation of DMD to different physics code, including MFEM, BLAST, AOE 3D, and Hyper. And again, the libROM syntax of DMD for MFEM is quite straightforward and easy to use. Once again, we see some outstanding numerical results on the DMD for several MFEM examples, where the original code can be found on our libROM webpage. So far we have introduced the ideas of projection-based and non-intrusive reduced order models and discussed some details to achieve the speedup. Now we are moving on to discuss some more details about the localization of the reduced order models for achieving better accuracy. So we have already seen that each type of reduced order models can be characterized by some matrix components. For example, the projection-based reduced order model is characterized by the basis matrix and the sampling matrix, and the dynamic mode decomposition is characterized by the basis matrix and the eigenpairs. If we use the same set of matrix for all the scenarios that we consider, it is a global reduced order model. However, if the solution behavior differs a lot among these scenarios, then it may not be a smart approach, since we may not have any efficient compression on the data to balance a good speedup and accuracy. Instead, we can use the local reduced order models, which is introduced to tackle this issue by assigning different reduced order model at different points in the parameter time domain. In this way, the snapshots are classified, which yields a better chance of efficient compression in the snapshot matrix, which in turn means faster and more accurate prediction in the solution. And this will allow us to tailor the reduced order model to be used for unseen parameters and produce higher generalization ability. But all these advantages are based on the assumption that we use the correct local reduced order model among all those retrained for prediction. So we will discuss two possible ways. The first way we will briefly mention is the time windowing and distance windowing approach for localization of the effective phenomena like the Lagrangian hydrodynamics. In the offline phase, instead of doing SVD directly on all the data, we will cluster this snapshot data into groups and use an appropriate indicator to do that. After that, we will build a reduced order model in each group, so we have multiple reduced order models. And in the online phase, we will use the same indicator to assign an appropriate reduced order model to locally approximate the dynamics, which means we use another reduced order model for each subinterval in the time domain. And in the distance windowing approach, the length of the subinterval depends on the parameter so that it can better locate the trust region of each local reduced order model. On the other hand, it may be a more interesting case for the generic parametric PDE setting. We can use the concept of parametric interpolation to make the reduced order model more robust. We take a DMDX as an example. The model is characterized by the basis and the eigenpairs. Suppose we consider a parameter space D, and we select some representative parameters with available snapshot data as training parameters. For example, these 5 points. Then we will construct the DMD matrix components at all these training parameters. At a testing point, we can interpolate each of these matrix components and use them for obtaining the DMD prediction formula tailored for that testing point. And as you can imagine, we can apply similar interpolation for all other testing points. Then we run into a familiar question. So how do we choose these training parameters? We can choose among the Latin hypercube sampling, the orthogonal sampling, random sampling, or the more efficient physics-informed greedy sampling. So it is explained in this short YouTube video on our libROM webpage. It is less than 10 minutes, but it's very informative. So we'll illustrate how this parametric DMD performs using the nonlinear heat conduction problem. We consider circular initial condition with 3D parameter, that is the radius and the coordinates of the center of the circle. As you can see, we trained with 5 training parameters, and the DMD was able to predict the solution quite accurately with around 1% relative error at all these testing parameters. And this parametric DMD can be used to accelerate the multi-query applications like inverse problems or optimal control or design optimization. So for an easy toy example, let's say we want to find out the parameters that produce the final time DMD temperature field, which match a target temperature field the best with this minimization problem. We will solve this minimization problem with differential evolution algorithm, which is derivative-free. It starts with an initial guess of the parameters, iteratively solves for an optimal solution, and eventually hits the stopping criterion, returns a final guess for the parameters. And in fact, this guess is quite close to the actual parameters, which is used to generate the target temperature. The relative difference in these parameters is just 2.3%. So I've covered different reduced order model techniques today, and this is the end of my presentation today. And if you are interested in knowing more about the methods and the results in our work, please check out our libROM webpage and the GitHub repo. Thank you for your attention, and any comments or questions we welcome.